So today I'm taking class on behalf of Azam sir. So we will start with the telescope. Is all like optical instrument started, like microscope and all completed in your class?
The telescope is completed.
So can anyone tell what is the difference between microscope and telescope? Any idea? Can you see the screen?
Yes, sir.
One is differences like telescope is used to see distant objects, right? And with the help of microscope, we see nearby objects. That is okay. Apart from that, any difference? Do you have anyone having any idea about telescope, or it's very like so the major difference we all know in the construction, that is obviously the construction differs. In microscope we have larger eyepiece as well as a smaller objective. Sorry, in microscope we have larger objective and larger eyepiece, right? And a smaller objective. In case of telescope, we will have larger objective and a smaller eyepiece. That is difference in the construction. But the major thing is that you have to remember that microscope basically used to amplify the objects, right? You are seeing the amplified image, magnified image, like. But in case of telescope, telescope doesn't do any kind of magnification. What it does is it will form image of a distant object at the desired point where you want it, whether you want the image at the infinity, or whether you want normal vision, or whether you want near point vision. According to that, it will project image of the distance object at a particular position. So it will not do any kind of magnification. It only helps us to see the distant objects clearly. Getting my point? So this is the difference. Generally, generally we don't keep in mind that generally we have a perception that like microscope and telescope used to magnify objects. This is not so. This is not in the case of telescope. Telescope doesn't do any kind of magnification. All right. So now let us all join. So let us start with the telescope. So first you see if we see about the definition part. So in the definition you can write telescope. Telescopes are optical instruments. You can write the definition. Telescopes are optical instruments which are used to see distant objects, which are used to see distant objects clearly. Which are used to see distant objects clearly. Full stop. Generally, what a telescope does, it projects distant, it projects distant objects to a desired position. It projects distant objects to a desired position, like in bracket you can write normal position, or at least distance of distinct vision, normal position, or at least distance of distinct vision, bracket close, according to our requirement. So now if you see the types of telescope, generally we have two kind of telescope, that is astronomical and terrestrial telescope. But most common is astronomical telescope, and in astronomical we also have two kind of there are two types, like refracting type and reflective type. But most important one is refracting type telescope, which is also in your syllabus. So most of the, in 90% cases, question will be asked from the refracting type of telescope, which we are going to study detail. We are not going to study about terrestrial telescope. It actually includes, it's kind of like it's having three lenses and all, so we don't have to go in detail about terrestrial telescope. Now start with refracting telescope, and we know, as same case with the microscope, we generally had two kind of uh, position, like we had two cases there, we have discussed there, when final image was formed at infinity and when final image was formed at least distance of distinct vision. There were two cases, right? In the case of microscope, same two cases we will discuss here. We will have separate two cases. First we will discuss final image at least distinct of distinct vision, then we will discuss final image at infinity, which is also known as normal adjustment. Getting all of you any doubt till now? I think this is a definition part. So all of you clear with the category of telescope? Generally we are going to study, we will study on the astronomical telescope, and in this we will be focusing, good evening, we will be focusing on refracting type of telescope on. Got it? All right.
Yes, sir.
Now if you see the definition of astronomical telescope, it is like, it is a refracting type telescope used to view astronomical objects like planets, stars, etc. So as the name suggests, astro comes basically, the name astro comes basically from astronomical objects like star, planets. So that is why the name is given an astronomical telescope, and it is mostly used to see celestial objects. So if you see the construction part, there is a difference of construction. Basically, it consists of two convex lenses at the end of a slide. So actually what happens in a telescope, generally we have a tube, and this tube contains two lenses fixed at different distances, separated by some distance with each other, and generally the distance between the two lenses is known as tube length, or length of the tube, which we are going to see in the coming section. So if we talk about the two lenses, these two lenses are named as objective as well as eyepiece. So objective and eyepiece, all of you know from the microscope. You have also studied about objective and eyepiece. Objective, that is nearer to the object, and eyepiece, that is near to the eye. So from that, the name is given as objective as well as eyepiece. All of you are familiar with the names. Now if we talk about the objective here, it will be larger, right? So generally if you want to see a distant object, right? So if you want to see a distant object, you want more and more light to be captured by the instrument. And if you want to capture more and more light, the facing lens which is facing the object should be of larger aperture, or should be of larger size, or should be larger. That is why objective of optical astronomical telescope is kept larger, or it is of larger aperture. So it is very crucial, or it is very important, that the objective of a telescope is larger, or it is of larger focal length, or you can say it is of larger aperture than eyepiece. This is the main difference if we talk about the first difference, and this is very important. So according to the definition, you can also see here, it is the convex lens of large focal length and large aperture. Aperture is large so that maximum amount of light can enter into it, and the image is bright. So more and more light you are getting, brighter will be the image. That is why its dimension is kept large as compared to eyepiece. Now if you talk about eyepiece, it is a lens of small focal length and small aperture. Aperture of eyepiece is small so that full light of telescope can enter into the eye. And obviously if the eyepiece will be of larger dimension, then it will not match with your dimension of the eye also. Getting my point? So if it is of comparable dimension with the eye, what will happen? Whole of the light entering from the objective and to the eyepiece will be uh, you know recepted by your eyes, right? No, there is no mismatch in this size, so whole of the light coming into the eyepiece will be uh, gathered by the eye, eye lens, or that all the image uh, will be, that is all the light rays will be used to form the image. So there will not be any loss of light. If the aperture of eyepiece could have been larger, then there was a chances of mismatch, and in that case we may lose some intensity of light. So this is the case. Now we will discuss the first case, that is when final images, as I have told you that there are two cases, there are two possibilities. One, when is final image at least distance of distinct vision, and the second will be the case when the final image is formed at infinity. So let us discuss the first case, when final image is at least distance of distinct vision. It means the final image is formed at a distance of 25 centimeter from the eye. So before that, we will use the magnifying power. We want to calculate the magnifying power of a telescope. So what will be the definition? You see, there will be two definitions. In case of least distance of distinct vision, there will be one definition of magnifying power, and there will be slight change in case of normal vision or final image is at infinity. So if you see here, magnifying power we can define as it is the ratio of angle subtended by image and object on the eye when image is at least distance of distinct vision. So Only thing you have to find the ratio of the angle subtended by image and object. See, the two things you have to remember is you have to take the ratio of the angle of the image as well as that of the object at the eye. The main thing is that in case of a telescope, we know that the object has large distance, so obviously we can treat the object is at infinity. So that is not in this definition, we don't have to concentrate on that. Automatically the object is at infinity, so only we have to keep in mind that we have to take the ratio of angle subtended by image as well as angle subtended by object at the eye. Now if you see the diagram here, uh, you see the first lens, that is called objective lens, and so here you can see so this is the objective lens which is of larger aperture as compared to the eyepiece, and you can assume that final of the object can be treated at infinity, right? Here we can assume that there is a celestial object which is at large distance from the objective, and light is coming from that object, and we know that when light is coming from a distant object, it can be treated as light is coming from infinity. So we have assumed that object distance for the objective will be at infinity. Now when it enters the objective lens, obviously because it coming from the infinity, it will converge at the focus of the objective, right? Obviously it should converge at the focus because light rays are coming parallel and coming from the infinity, right? So now what will happen, this distance, obviously when uh, the object distance is infinity, the image formed by a lens is its focal length. So the image distance will be equal to focal length of the objective, that is f naught. So all of you understand why we have taken v naught equal to f naught? Anyone having doubt, please ask. Why we have taken v naught equal to f naught? I think all of you should understood this. If anyone having any doubt, you can ask. All of you understood why v naught is equal to v naught? Because the light is coming from the infinity, and when parallel rays incident on a length, they converge at the focal length of the length. That is why v naught will be equal to f. So now we have taken the first image of the, or you can also say it's intermediate image. So first, it is also known as intermediate image. So the intermediate image or first image formed by the objective is b dash a dash. Suppose the object is AB like this. So the first image is A dash B dash. Got it? Now what will happen? This object, this image of object AB, so this image A dash B dash will act as object for the eye. This is the eye lens. So this will act as a object for the eye lens. Now here in the first case, we are considering the case that the final image is formed at least distance of distinct vision. It means, obviously, we can draw the diagram like this for the final image, and we have assumed that here the final image is formed at least distance of distinct vision, capital D. Got it? So we have drawn the image of A dash B dash. to draw that, we have produced it backward, and all are intersecting at A double dash B double dash. So the image of A dash B dash is A double dash B double dash, which is the final image of the object AB. Now we can assume that the angle made by this final image A dash B dash at the eye is beta, and the angle made by the object is alpha. You can see it from the diagram. Now what we have to do is, now our next task is to find magnifying power, right? To find magnifying power. So from the definition we know that magnifying power is the ratio of the angle subtended by the image at the eye. So here you can see the angle subtended by the image is beta.
अरे ये है क्लास है उसी के पार्ट
And the angle subtended by the object is alpha, right? So we will get the magnification m, that is equal to beta by alpha. Got it?
Yes, sir.
yes
So we will take the ratio of beta by alpha. Now how to find beta and how to find the alpha, that is the main thing. So to find the beta, what we have to do, we have to see in the triangle A dash B dash O2. So we will see the triangle A dash B dash O2, right? This triangle A dash B dash. So here in this triangle, so here in the triangle, if you see the, you wanted to find the angle beta, right? So you have to see in the triangle A dash B dash O2. So it is clear from the diagram that you can write tan beta. What will be the tan beta? Tan beta will be equal to A dash B dash by O2 B dash, right? This will be the tan beta. And similarly, if you see here, in this triangle, this angle is alpha, right? So from this diagram, you can find the tan alpha also. What will be the tan alpha? Tan alpha will be equal to A dash B dash divided by O1 B dash, right? That will be the tan alpha. So now we know that we are using paraxial rays, so all the angles alpha and beta are small. So tan alpha can be written as alpha and tan beta can be written beta. This all you know from the microscope. We have also used in the microscope also. So that all of you can understand that here angles are small, so we can use these applications. So obviously we have taken tan beta is equal to beta is this, and tan alpha will be equal to this. So now what we can do, we can take the ratio, and what is the ratio? That is m equal to, actually that is m equal to beta by alpha, right? So So beta by alpha, we have put the value of beta, that is A dash B dash by O2 B dash, and the alpha is A dash B dash by O1 B dash. So from there, A dash B dash will be cancelled out, and you will get M is equal to O1 B dash by O2 B dash. Now from the diagram, you can see that what is O1 B dash. If you see here, O1 B dash is V naught, right? So obviously O1 B dash is equal to F naught. So and V naught, and O2 B dash, you can see here what is O2 B dash. Obviously distance of the distance from the eyepiece. So you can take it as UE. So O2 B dash will be UE and O1 B dash will be PO. So in this part, anyone having any doubt, please ask. Anyone having any doubt, please ask. Or we have taken O1 B dash is equal to V naught and O2 B dash as minus UE. So anyone having any doubt in this?
No, sir.
All right. So now what we have to do is we have to put the values in the formula. So for M, we will put the value of O1 B dash, which was F naught, and O2 B dash, which was minus UE. So we got the magnification like this. Now how to find F naught by UE? We don't know F naught. We don't know the value of UE, right? F naught is known generally, but we don't know UE. So to find the UE, that is distance of the image from the eyepiece, we will apply the length formula. And from the length formula, we know that 1 by V is equal to 1 by V minus 1 by U, 1 by F. So we will apply the length formula and we'll put the values. So we'll get it as 1 by V minus 1 by U is equal to 1 by F, and we'll put the value of UE. So we will get it as, and we also know that the image is formed at least distance of distinct vision. So here we have taken minus a small d, but generally if you see in the books, generally it is taken as capital D. But anyway, we can use it as small d, but you in 90% cases it is capital D is used, right? So no worries if you are getting the formula somewhere capital D, that is the same thing. So now putting the value of V is minus D. Obviously the all image and objects all are in the left direction, so we are taking minus sign, and from the eyepiece the image is formed at this distance of distinct vision, so we have taken minus D. Now put those values, we will get the value of UE, which is 1 by U is 1 by FE plus D. So from here we will get the value of UE as like this. Now we wanted to find UE, right? So then we can find the magnification from this formula. We have to put the value of UE, so you will get F naught minus F naught into value of UE is this. Actually the magnification was, what was that? Minus F naught by U. So you can also take it like minus F naught to 1 by U, right? So you put the value of UE, which is this 1 by FE plus D. That is how you get M is equal to minus F naught by FE plus D. It's better to remember by capital D. Generally, in the books you will see it as capital D. So minus F naught by FE 1 plus FE by D. And obviously we know that final image is formed that is inverted, right? So that is why we are using minus sign. It shows this final image is inverted. And if there is any kind of D in the formula, if sometime you don't remember the formula, if you see there is capital D in the formula, it means the final image is formed at least distance of distinct image. Sometimes we may confuse what was the formula of magnifying power for the this distance and what was for the image at infinity. So whenever you're getting capital D in the formula, you should automatically get an idea that it is for this distance of distinct. In case of final image at infinity, you will not get capital D in the expression. Getting my point? So this is how you can remember the formula. So the final formula for magnifying power is minus f naught by ap 1 plus ap by t. So anyone having any doubt till now? Please ask.
No, sir.
So you practice this formula doing the question, you will remember. So it is very useful to remember the formula because most of the times you will be given objective focal length, eyepiece focal length, and you will be having to find the magnifying power. So for that case, we have to do online. Now, if you want to find the length of the tube, so what is the length of the tube? Actually, this is the length of the tube. The distance between the two lenses is known as length of the tube. So it is clear from the diagram that f naught plus ue. This will be the length of the tube, obviously. So from the diagram, we can say that length of the tube will be, and obviously you have to take magnitude, right? So length will be f naught plus ue, the tube of the telescope. Understood? So we will use this formula to find the length of the examples also. So this was the first case when the final image was formed at D, that is least distance of distinct waves. Now we will discuss the second case, that is when final image is formed at infinity. So sometimes also you will get that find the magnification or magnifying power when the final image is, when the eyes maximum strain. Sometimes you will have kind of language is that find the magnification for which eye is maximum strained. Getting my point? Maximum strain. So maximum strain, what is the case? Can anyone give an idea? What do you mean by maximum strained and minimum strained or relaxed? Anyone having any idea? If you have asked,
It is far from the near point of the eye.
that is okay. But in the question, they will ask you find the magnifying power of a telescope for the case when or the image is formed such that the eye is maximum strained. Then what you will understand, is it normal vision or is it least distance of distinct vision? What case you will consider if they will say?
Images beyond these distance of these distance of distinct vision.
Correct. When the language is maximum strained, it means final image is formed at these distance of distinct. In case of D, final image at capital D, the eye is maximum strained. And when in the question it is asked that find the magnification for the case when eye is relaxed, it means you have to consider the case of final image at infinity. So it will be useful for both microscope as well as telescope. In case of microscope, they can also use the same language. Understood? So every time they will not say that find the magnification for least distance of distinct vision and find the magnification for when final image is at infinity. No. Sometimes they will ask you like that. You see the previous year question, they have kind of language has been used in the question. So you have to remember that. Maximum strain means at least distance of distinct vision. Relaxed eye means final image is at. Got it? So now if you say the case 2, that is final image is at infinity, that is normal adjustment or eye is relaxed. And you can also see, you can observe in normal day-to-day life that when you see, when you see nearby objects, like when you reading a book and you are keeping the paper more and more close to your eyes, you will feel like that your eyes are getting more strained. And when the objects are far away, it's easy to kind of eyes getting less kind of, strain. You will feel that if you observe closely. So in day-to-day life also we can observe that. Now coming to case 2, that is final image at infinity. So in this case, what will be the magnifying power? It will be the ratio of angle subtended by uh, image and the object when both are infinity, right? Here final image is also at infinity. So it is the ratio of the angle subtended by image and the object when both are at infinity. Now if you see the diagram is most 90% same. Just what you have to do is, here you will not show any final image. Just put the just keep these rays parallel so that final image is formed at infinity. The initial diagram will be same. The same object is like AB, and same object is AB, and so final image to form at infinity, this image, intermediate image A dash B dash, must be at the uh, focus of the eyes, right? Sometime you must remember that in some time in question, maybe they will ask about the nature of the image of intermediate image, right? So if you see the nature of intermediate image, that is real as well as inverted, right? You should remember that. And in case of microscope also, remember the nature of the, you should remember nature of intermediate image. Sometimes they may ask what is the nature of the intermediate image formed in the case of astronomical telescope, or in case of microscope, compound microscope, or so kind of, we should remember. So this is the case here. The left part is same. The main change is here is, if you see here, what is the difference? The final image was formed at, here the final image was formed at infinite least distance of distinguisher, capital D, and here final image is getting at infinity. So this is only difference, other things are same. So for this image to be at infinity, obviously A dash B dash must be at the focal length of the iris. So now what we have to do, again we have to apply the same formula. We have to get the magnifying power. For that we have to take ratio of beta and alpha, and in the same way we can define beta A dash B dash by 2, same as previous case, and we can define also alpha, same as previous case. So you will get the ratio O dash B dash by O2 B dash. So O dash O1 B dash, that is clear from the diagram. We know that O1 dash B, this one is the obviously V naught, which is F naught. So that is clear. O1 B dash is F naught, and O2 B dash is also clear here. We don't have to apply the length formula. Obviously, for the final image at the infinity, O2 B dash should be equal to focal length of the eye. So here we have put that O2 B dash is FE. So obviously we will put both in the formula. We will get M equal to F naught. If you remember what I have told you, when in the final formula of magnifying power, if it is of least distant of distinct region, there must be capital D in the expression. Here there is no capital D in the expression, so you can automatically have an idea that minus if not MEB is the formula for magnification at infinity. There is no capital D in the expression. Sometimes we get overlapped. What is the formula for capital D and what is the formula for infinity? So for least distance of distinct region, there must be an expression of D in the final expression of magnifying power, and in case of normal vision, there will not be any D in the expression. So here it is minus if not by F. So this is the formula for normal vision or relaxed eye or final image. Got it? Obviously, length of the tube, what is will be that? V naught y, same as the previous formula. The difference is we have put U naught equal to Fe here. This F naught remains same. So till now, anyone having any doubt, please ask. So that we can go ahead to the question. Anyone having any doubt?
No, sir.
Now we can do the example based on optical telescope. So let us see. All of you can try on your pen and paper, then you can see the answer. So all of you try this question first yourself. All of you try this question yourself first, then we will go to the solution. All of you try and tell me the answer. Any answer? Have anyone got any answer?
What does K 10 centimeter mean?
10 centimeter, not A. Focal length is given as, I think it is given as 140,
Okay, sir.
not K, 140 centimeter. You have to find magnifying power for both the cases, for least distance of distinct vision and for the final image at infinity. Solve it quickly. Anyone got any answer? No one got any answer. Are you trying? What you have to do? Only you have to apply the formula in first case F naught by Fe 1 plus Fe by T. In the second case, what is the formula? Minus F naught by F. Formula apply. Get the result. Let us see. Case of final image at normal, at least distance, you will apply this formula F naught by Fe 1 plus Fe by T, and you will get the magnification as minus 20 for least distance. And in case of normal adjustment, minus F naught by Fe, so minus 2. In this case, you will get it at minus 33 point. So obviously, magnification is more in case of this distance of distinct. For normal case, it is minus 28, and for least distance of distinct, then it is 33.6. Got it? All right. Okay. Now see one more question. Try this
1
one.
minute, sir. Can you scroll up?
दोबारा
No, can you say, show me the answer of the previous question? Second count.
Okay. 33.6. What will be the unit of magnification?
Centimeters.
Centimeter, right? Anyone else?
Unitless, sir.
Yes, correct. It should be unitless. There is no unit of magnifying power. Got it? So in hurry, sometimes we give the unit to the magnifying power, and whole of our effort goes wrong when you are getting unit in your answer. You must be careful. Got it? Should we move ahead?
Yes, sir.
Alright. So now see the question based on NCRT, so take it as homework. This question of NCRT. All of you can have this question in short. Keep it as homework. I'm not going to solve this. You want to same the formula you have to apply. It's not by FB. You see in the question objective focal length given, and you have to find magnification for normal case. For normal case for that, you have to apply FE. Then for the second case, all right. So both of you try it as a homework. This question. Anyone want me to solve this question? What will you do in the homework? Okay, moving ahead.
Sir, can you show the second part of the question?
We have reflecting type of second part.
Yeah, how to do that? Second part.
It says if this telescope is used to view moon, what is the diameter of image of moon formed by the objective? Diameter of moon is actual diameter is this, radius of linear orbit is this. So here you can use this formula like C. Suppose this is the moon and the telescope is used to see image of moon. So obviously this distance will be the diameter for sure. This will act as the diameter, and suppose the image formed by this is alpha, and the image formed by the image is beta. We have assumed that. So from there, please anyone check your microphone. It is on. Please off. So now what will happen from there? What you can write? Obviously, this angle and this angle should be the same. So from there, what you can write? What is the value of alpha? Suppose the diameter of the moon is d, and this distance is the distance of the moon from the observer. So you can write angle alpha as, arc formula. Angle is arc length upon, what is angle? Angle is arc length upon distance, right? So from there, you can get it. Alpha is d1 by r, and suppose d2 is the length of the image or diameter of the image. So what you can write? D should be equal to, and obviously this should be equal to f focal length. We know that for the normal adjustment, the image must be at the focus. So from there you can write angle beta is equal to d by f. So from here you can find the diameter of the image. Got it? Understood? Anyone having any doubt, please ask. All right. Moving to the next type of telescope, that is reflecting telescope. That is not so important. Generally, you will be asked from the reflecting type only. So let us have some discussion based on that. So this is the reflecting type of telescope. In this, just to understand, generally the questions are not asked. So what is the advantage of how we have taken the reflecting telescope? So in reflecting telescope, generally we are using mirrors. So why reflecting? Can anyone explain why reflecting type telescope is used? What was the need of that? We were getting the magnifying power and we were getting the desired result from the astronomical telescope. Then what is the need of this reflecting telescope? Why it come into existence? Why we needed it? Can anyone explain? Anyone having any idea? See, what happening is in case of astronomical telescope, that is refracting telescope, we were using the two lenses, right? So in this starting of uh, lecture of optics, or at the end of lens lecture, you may have heard about aberration, right? I don't know why it is getting erased itself. You may have heard about aberration. I don't know why it is deleted by itself. When I'm writing anything, it's not deleted. So aberration, right? So you may have heard about like when lenses can have different focal length for uh, different colored light. Have you heard about that?
Yes, sir.
So when you are using lens, what happens is for different colors of light, that for different colors of light, focal length of is different. You know, wavelength of light rays different for wavelength of the lens becomes different for different color light. So to avoid that, so what happen actually is that different colors of light converge at different points. So to avoid that, we are here we are using the mirror. So in the mirror, that problem uh, is reduced. In case of mirror, we don't have that kind of problem, that is converging different colored light at different points. That is why to have better quality of image, as well as uh, no loss of light intensity, we are using reflecting type of microscope, telescope, sorry. So here we are using two mirrors in place of two. Where one mirror is this one. So basically we are using two mirrors to avoid that kind of. Here you can also get the same formula for magnification as m is minus f naught by fe, and you will get it as minus f naught is minus r by 2, f is fe, and focal length will be obviously it is the mirror, so it will be minus r. All right, so this was all about telescope. So only thing you have to remember the formula. If you remember the formula, and if you know in case of board exams, you will be asked to draw the diagram for the construction and working. So we'll be having to draw the ray diagram, and you have to derive the result from the uh, magnifying power. So you will be asked to draw construction and working of the astronomical telescope and derive the expression for the magnifying power. So you have to draw this diagram, the previous diagram, and then what you have to do is you have to derive the expression for magnifying power by taking the ratio of beta and alpha in the same way we have done. So generally, these are asked in 5-mark questions in case of boards, and also in competitive exams, you will have based on magnification. In 85% case, you will get the question based on magnification. Somehow they will ask you the magnification, and if you remember the formula, you will get the question. So this was all about telescope from my side. So anyone having any doubts, you can ask. Otherwise, I will move to the next topic, that is prism. So should we go ahead?
Yes, sir.
Okay. Next is prism. Can anyone define what is a prism? What do you understand by prism? Anyone? What do you mean by prism?
Sir, it is a glass structure made of two triangular surfaces and three rectangular surfaces.
Yes, actually it is a transparent. When a transparent medium, or you can say when a transparent medium is in between two surfaces which are inclined at some angle. So this kind of a structure, you can define it like it is, you can say prism is a wedge shaped portion of a transparent refracting medium bounded by two plane surfaces or faces inclined to each other. So whenever a transparent portion or transparent object or a transparent medium is such that it is bounded between two inclined surfaces. So basically it is a 3D diagram of a prism. Generally what we see this. Actually this is the cross section. You draw a cross section of any part. So generally we study the cross section of this. The actual image is this one, but we use this for simplicity. And we all know what is refracting angle, the prism angle. The lower part is known as base. This one is base. This is the refracting surface, and this angle is known as angle of reflection. So this way on, also called refracting. Now, if you see the very important thing is deviation produced by. So what happens is that when a light ray passes through a prism, it will not pass straight forward, right? It will obviously it will bend like this. So suppose a light ray incident like this, and it passes like this inside the prism and get outside like this. So obviously, if you see the original direction of the ray was this, and finally it is moving along this direction. So this is the angle of deviation. If you see light rays rotated from this direction to this direction, it means light rays deviated. So that is known as angle of deviation. That is the angle between the direction of incident light as well as direction of emergent light. And that is become very important to calculate in case of prism. So what we have to do is draw the diagram like this. This is the incident ray and all. The values are shown here. If you see, it is the angle of incidence. R1 is the angle of refraction, and N1 and N2 are normal to the prism. Now, what we have to do is, we have found I minus R1, and then we found E minus R2. Call this angle as E. So we know that delta is the exterior angle of a triangle, and we know that exterior angle of a triangle is equal to sum of posterior angles or sum of opposite angle of the triangle. So from here we can write delta will be equal to I minus R1 plus E minus R2. This is from the geometry of the figure. We can write delta. Same is written here. Delta will be equal to I minus R1 plus E minus R2. Then you can rearrange it like this: I plus E minus R2 plus R2. This is the deviation produced by the prism. Now, if you see in the triangle BCD, obviously what we can write? We can write R1 plus R2 plus this angle. If you say this angle as D, so obviously R1 plus R2 plus D will be equal to 180. So we can use this formula. So from there, now if you see in quadrilateral ABC, you see the quadrilateral ABDC. So obviously two angles are 90 degree. This angle is 90 degree. This angle is 90 degree. It means the sum of this angle and sum of this angle. Sum of this angle and sum of this angle should be 180 degree. So from that you can write as E plus D is 180 degree, and using this one we'll put the values R1 plus R2 plus D, that will be equal to A plus D, and from there you will get R1 plus R2. This is very important in the place. You have to remember that R1 plus R2 comes as A. Got it? All of you understood this? How we got R1 plus R2 equal to A?
Yes, sir.
Now the things become easier if you understand R1 plus R2 equal to A. Now things become easy. We know that delta was I plus E, minus R1 plus R2. So we put the value of R1 plus R2, that is equal to A. So we got the deviation equal to I plus E. So now leave it here. Now we will directly move to calculation for minimum deviation. So delta is equal to, you can remember, I plus E minus A. Alright. Now moving to the minimum deviation. Then I will come to the previous part, delta is equal to mu minus 20. So first we will divide. We know that delta is equal to, we got the result delta is I plus E minus, right? there is an issue in the board, so I am explaining you in separate board. All right. So what we got? We got the formula for delta. That was for delta is equal to I plus E minus A, right? So let the board reload. So we come to the formula delta is equal to I plus E minus A. Now there is a condition you will get a from experiment. Generally, when we do an experiment has been done to find the relation between deviation and angle of incidence. So it was found that the graph of delta versus I, the graph of delta versus I was found like this. And if you see this graph of delta versus I, you can see that for two angles, suppose you are taking one angle as I1, one angle as I2, so you will get that there are same deviation delta for two angle of incidence. If you see here, for two angle of incidence I1 and I2, you are getting same angle of deviation delta. So it was also found that actually what happens. So actually why this is two different values? We are getting the same deviation. So actually what happens is that the mirror is symmetric, right? You see mirror is a symmetric. So actually what happens, there are two as suppose this angle is I1 and suppose this angle is I2. So what happens is that if you see from the left side, you observe from the left side, the angle is I1, and if you observe from the right side, if you know if light is incident from left side and the angle is I1, and what was the emergent angle in the first case, let us put it as incident angle for the second case. So you will get the same deviation. Getting my point? The emergent angle of the first case can become as incident angle for the second case, but deviation will be same in the both case. That is why we are getting for two angle of incidences I1 and I2, you will get the same angle of deviation. That is the thing here. So it was found that for a particular angle of incidence, that is I equal to I1 equal to I2 or I equal to E, you can say that it was found that angle of deviation was minimum from the graph. So that minimum deviation was only for angle of when angle of incidence was equal to angle of emergence. In that case, it was found that deviation is minimum. So from that we can write that delta minimum. What will be the delta minimum? That is I plus E minus A, and if you put it like this, I plus E should be equal to I. So I should be equal to E minus A. So from here you will get delta is equal to 2i, delta minimum to 2i minus a. So from here you can write I will be equal to a plus delta a by 2. You can put the value of I as a plus delta a by 2. Now what you can do? Now what we can do is that you can see here, if you got that one, now you can find the I. So now if you put the value of I over here, what you will get? Also we know that in case of this formula we got, and also we know that this result we have already got, and also we know that R1 plus R2 equal to A. So for R1 equal to R2, you can write it like this. And from here, we know from Prism formula, you can apply law of reflection like this, not Prism formula, from Snell's law. From Snell's law, you can get it like this, and you can put the value of I. You get I is equal to A plus delta M by 2, and R1 equal to A by 2. So if you put those values, you will get N equal to N or mu refractive index of the prism equal to sine A plus then M by 2 by sine. So all of you understood this one, how we got the formula? Anyone having any doubt, please ask.
So can you see how you got a plus delta minimum by 2?
Sorry,
So can you say the sign part?
this one.
So
We know the delta minimum. For delta minimum, I is equal to E, right?
yes,
This you understood. And we put the formula E equal to I, so we got this. And from here, we will got I. I is A plus delta M by 2. So this you understood. Now we know that R1 plus R2 equal to A, and obviously if I is equal to, if I is equal to E, if angle of incidence equal to angle of emergence, so obviously we can write R1 will be equal to R2, right? If R1 equal to R2, then you can get R1 will be equal to A by 2, and this you understood. You were asking this one.
yes, sir.
This one you can apply this Snell's law at the mirror. If you see here you can apply Snell's law at the mirror. Here you can apply this Snell's law. 1 into sine I, 1 into sine I will be equal to mu into sine R1, right? So from here you will get mu equal to sine I by sine from Snell's law only. Got it?
Yes, sir.
So we have put that. We have put the value of I, and we have put the value of R, which is A by 2. So you got sine A plus delta M by 2 by sine. Got it?
Yes,
This
sir.
is now what happens. So this is the general formula. This is the general formula for refractive index of the prism in case of minimum deviation. But what happens if the prism is thin? In some cases, if prism is thin, so I will explain you. What will happen if prism is thin? If prism is thin, so this angle will be very small. So you can directly write, you can remove sine, right? If angle is small, sin theta is equal to theta. So you can write n equal to delta m plus a by 2 divided by again a by 2. You can remove sine because for a small angle sin theta equal to theta. So from here what you will get? You will get n equal to a plus delta m divided by a, and from here you will get delta minimum equal to n minus 1 into a. If you rearrange, you will get this. Got it? You will get delta m equal to n minus 1. So this was the result which I have skipped earlier. This result should be out after the formula of delta minimum. I don't teach before the formula of delta. So this is the result, delta minimum is equal to a into n minus 1. Actually, this can be easily derived from this. Got it? So if angle is small for thin prism, you can directly put it like this and you will get delta equal to n. For thin prism, what do you understand by thin prism? Thin prism means the angle A should be between 1 degree to 5 degree, not more than that. If angle A is between 1 degree to 5 degree, then prism is treated as thin. Generally, it is very confusing among a student when to consider a prism. With thin prism means angle, refracting angle should be between 1 degree to 5 degree. Otherwise, you can not apply this form. If prism is thin directly, you can apply this form. Got it?
Yes, sir.
So this were all the formula for minimum deviation as well as for normal prism as well as for thin prism. Now I have some question based on that. Like let us see what time permits. Here you have to calculate the refractives of the material, which is angle of minimum deviation is 60 degree. So here the prism is calculate the refractive index of the material of equilateral prism. So can you apply the thin prism formula? Can we apply delta equal to n minus 1 into a here? Can we apply this one? Here we cannot apply this formula, right? Because it is equilateral prism. It means angle of prism is 60 degree. Got it? So you have to apply general formula, this formula, to find the refractive index. Understood?
Yes, sir.
Yeah. This way. Now the things are okay. Angle of prism is given. Delta minimum is given. You have to find the refractive index. Directly apply the formula. You will get. Again, a question is that area of light passed through equilateral prism such that the angle of incidence is equal to angle of emergence. If angle of emergence is 3 by 4 times the angle of prism, calculate the angle of deviation. Calculate one angle of deviation and refractive index. So here actually angle of incidence is equilateral prism is given. So obviously A will be 60 degree and angle of incidence is equal to angle of prism. It is given in the question. So and how it is 45 degree. So you can put the values. It is also given in the question that I equal to E equal to 3A by 4, right? So from here you will get I equal to 45 degree and you can put this in the formula. You will get delta. Similarly, you can find the refractive index by this formula. Delta minimum we know we have calculated 30 degree and A by 2 all we know by putting the formula we will get the refractive. Got it?
Yes, sir.
So this is the last question. Let us see. Area of light PQ is incident at an angle of 60° at the face AB of a prism of angle 30°, as shown in the figure. The remaining out of the prism angle is 30°. With calculate angle of emergence of the prism and refractivity. It is given in the question, and we have to find refractive index of the prism as well as. So what we have to do is, let us see here, I is given, angle of incidence is given, angle of prism is given, delta is given. We have to find E. So for that you can directly apply this formula. Delta is equal to I plus E minus A, and you can find the angle of emergence. And in the second case, again you have to apply Snell's law. Here you don't have to apply mu is equal to sine E plus del M by 2 by A by 2. Here we don't know that it is minimum deviation, right? So you have to find the refractive index, you have to apply Snell's law, and then you can find the refractive. So any doubt till now? I think all of you understood the things. Anyone having any doubt? All right, so I'm ending the class here. For today's class, we have done with the prism and we have done with the telescope. All right, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.